Hello friends, in our last discussion we talked about the comparator and some of its important applications. Today in this lecture we are going to wind up the discussion on analog circuits with summing amplifiers, integrators and finally differentiators. The summing amplifier is an application of the inverting op amp configuration. The averaging amplifier and the scaling amplifier are variations of the basic summing amplifier. A summing amplifier has two or more inputs and its output voltage is proportional to the negative of the algebraic sum of its input voltages. A two input summing amplifier with unity gain is shown in figure, but any number of inputs can be used. The operation of the circuit and derivation of the output expression are as follows. Two voltages V in 1 and V in 2 are applied to the inputs and produce currents I 1 and I 2. Using the concepts of infinite input impedance and virtual ground, you can determine that the inverting input of the op amp is approximately 0 volt and has no current through it. This means that the total current I t which goes through RF divides into I 1 and I 2 at summing point A as indicated. So, I t is equal to I 1 plus I 2. Since V out is equal to minus I t into RF, the following steps apply. V out is equal to minus I 1 plus I 2 into RF and is equal to minus V in 1 over R 1 plus V in 2 over R 2 into RF. If all three of the resistors are equal, that is R 1 is equal to R 2 and is equal to R, then V out is equal to minus V in 1 over R plus V in 2 over R into R, and this comes out to be minus V in 1 plus V in 2. This equation shows that the output voltage has the same magnitude as the sum of the two input voltages, but with a negative sign indicating inversion. This figure here shows the unity gain summing amplifier with n inputs and all resistors having the same value. A general expression for output voltage is given by this equation, where V out is equal to minus V in 1 plus V in 2 plus V in 3 and so on till V in n. Summing amplifier with gain greater than unity. When RF is larger than the input resistors, the amplifier has a gain of RF over R, where R is the value of each equal value input resistor. The general expression for the output is given by this equation. V out is equal to minus RF over R into V in 1 plus V in 2 plus V in 3 so on till V in n. As you can see, the output voltage has the same magnitude as the sum of all the input voltages multiplied by a constant determined by the ratio minus RF over R. Averaging amplifier. A summing amplifier can be made to produce the mathematical average of the input voltages. This is done by setting the ratio RF over R equal to the reciprocal of the number of inputs. Rf over R is equal to 1 by n. You obtain the average of several numbers by first adding the numbers and then dividing by the quantity of numbers you have. Examination of the summing amplifier equation with gain greater than unity and a little thought will convince you that a summing amplifier can be designed to do this. Applications. DA conversion is an important interface process for converting digital signals to analog signals. An example is a voice signal that is digitized for storage, processing or transmission and must be changed back into an approximation of the original audio signal in order to drive a speaker. One method of D to A conversion uses a scaling adder with input resistor values that represent the binary weights of the digital input code. Although this is not the most widely used method, it serves to illustrate how a scaling adder can be applied. A more common method for D to A conversion is known as the R over 2R ladder method. The R oblique 2R ladder is introduced here for comparison, although it does not use a scaling adder. Figure here shows a 4-digit digital to analog converter. This type of digital to analog converter is called a binary weighted resistor. The switch symbol represents transistor switches for applying each of the 4 binary digits to the inputs. The inverting input is at virtual ground, and so the output voltage is proportional to the current through the feedback resistor RF. The lowest value resistor R corresponds to the highest weighted binary input, that is 2 to the power 3. All of the other resistors are multiples of R and correspond to the binary weights 2 to the power 2, 2 to the power 1 and 2 to the power 0. Integrators and differentiators. An op-amp integrator simulates mathematical integration, which is basically a summing process that determines the total area under the curve of a function. An op-amp differentiator simulates mathematical differentiation, which is a process of determining the instantaneous rate of change of a function. It is not necessary for you to understand mathematical integration or differentiation at this point in order to learn how an integrator and differentiator work. Ideal integrators and differentiators are used to show basic principles. Practical integrators often have an additional resistor in parallel with the feedback capacitor to prevent saturation. Practical differentiators may include a resistor in series with the comparator to reduce high frequency noise. The op-amp integrator. The ideal integrator is shown in the figure here. Notice that the feedback element is a capacitor that forms an RC circuit with the input resistor. To understand how an integrator works, it is important to review how a capacitor charges. Recall that the charge Q on a capacitor is proportional to the charging current IC and the time t. So, Q is equal to IC into t. Also, in terms of the voltage, the charge on a capacitor is Q is equal to C into Vc. From these two relationships, the capacitor voltage can be expressed as Vc is equal to IC over C into t. This expression has the form of an equation for a straight line that begins at 0 with a constant slope of IC over C. Remember from algebra that the general formula for a straight line is y is equal to mx plus b. In this case, y is equal to Vc, m is equal to Ic over C, x is equal to t and b is equal to 0. Recall that the capacitor voltage in a simple RC circuit is not linear but is exponential. This is because the charging current continuously decreases as the capacitor charges and causes the rate of change of the voltage to continuously decrease. The key thing about using an op-amp with an RC circuit to form an integrator is that the capacitor's charging current is made constant, thus producing a straight line voltage rather than an exponential voltage. Now, let us see why this is true. In the figure shown here, the inverting input of the op-amp is at virtual ground. So, the voltage across Ri equals Vn. Therefore, the input current is In is equal to Vn over Ri. If Vn is a constant voltage, then In is also a constant because the inverting input always remains at 0 volt, keeping a constant voltage across Ri. Because of the very high input impedance of the op-amp, there is negligible current at the inverting input. This makes all of the input current go through the capacitor. So, IC is equal to In. The capacitor voltage. Since In is a constant, so is IC. The constant IC charges the capacitor linearly and produces a linear voltage across C. The positive side of the capacitor is held at 0 volt by the virtual ground of the op-amp. The voltage on the negative side of the capacitor, which is the op-amp output voltage, decreases linearly from 0 as the capacitor charges. The voltage Vc is called a negative ramp and is the consequence of a constant positive input. The output voltage. As shown in this figure, V out is the same as the voltage on the negative side of the capacitor. When a constant positive input voltage in the form of a step or pulse is applied, the output ramp decreases negatively until the op-amp saturates at its maximum negative level. Rate of change of the output voltage. As you have seen, the rate at which the capacitor charges and therefore the slope of the output ramp is set by the ratio IC upon C. Since IC is equal to Vn over Ri, the rate of change or slope of integrator's output voltage is delta V out over delta T. Therefore, delta V out over delta T is equal to minus Vn over Ri into C. Integrators are especially useful in triangular wave oscillators. The practical integrator. The ideal integrator uses a capacitor in the feedback path, which is open to DC. This implies that the gain at DC is the open loop gain of the op-amp. In a practical integrator, any DC error voltage due to offset error will cause the output to produce a ramp that moves towards either positive or negative saturation depending on the offset even when no signal is present. Practical integrators must have some means of overcoming the effect of offset and bias current. Various solutions are available such as chopper stabilized amplifier. However, the simplest solution is to use a resistor in parallel with the capacitor in the feedback path as shown here. The feedback resistor RF should be large compared to the input resistor Rn in order to have a negligible effect on the output waveform. In addition, a compensating resistor Rc may be added to the non-inverting input to balance the effects of bias current. The op-amp differentiator. An ideal differentiator is shown in the figure here. Notice how the placement of the capacitor and resistor differ from the integrator. The capacitor is now the input element and the resistor is the feedback element. A differentiator produces an output that is proportional to the rate of change of the input voltage. To see how the differentiator works, apply a positive going ramp voltage to the input as indicated in this figure. In this case, IC is equal to IN and the voltage across the capacitor is equal to Vn at all times because of virtual ground on the inverting input. From the basic formula, Vc is equal to Ic over C into T. The capacitor current is given by this equation where Ic is equal to Vc over T into C. Since the current at the inverting input is negligible, IR is equal to Ic. Both currents are constant because the slope of the capacitor voltage, that is Vc over T, is constant. The output voltage is also constant and equal to the voltage across Rf. Because one side of the feedback resistor is always 0 volt or virtual ground, V out is given by this equation where V out is equal to IR into Rf and is equal to Ic into Rf. Therefore, V out is equal to minus Vc over T into Rf into C. The output is negative when the input is a positive going ramp and positive when the input is a negative going ramp as illustrated in figure. During the positive slope of the input, the capacitor is charging from the input source and the constant current through the feedback resistor is in the direction shown. During the negative slope of the input, the current is in the opposite direction because the capacitor is discharging. Notice in equation V out is equal to minus Vc over T into Rf into C that the term Vc over T is the slope of the input. If the slope increases, V out increases. If the slope decreases, V out decreases. The output voltage is proportional to the slope or rate of change of the input. The constant of proportionality is the time constant Rf into C. The practical differentiator. The ideal differentiator uses a capacitor in series with the inverting input. Because a capacitor has very low impedance at high frequencies, the combination of Rf and C form a very high gain amplifier at high frequencies. This means that a differentiator circuit tends to be noisy because electrical noise mainly consists of high frequencies. The solution to this problem is simply to add a resistor Rn in series with the capacitor to act as a low pass filter and reduce the gain at high frequencies. The resistor should be small compared to the feedback resistor in order to have a negligible effect on the desired signal. Figure here shows a practical differentiator. A bias compensating resistor may also be used on the non-inverting input. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learnt that the output voltage of a summing amplifier is proportional to the sum of the input voltages. An averaging amplifier is a summing amplifier with a closed loop gain equal to the reciprocal of the number of inputs. Integration is a mathematical process for determining the area under a curve. Integration of a step input produces a ramp output with a slope proportional to the amplitude. Differentiation is a mathematical process for determining the rate of change of a function. Differentiation of a ramp input produces a step output with amplitude proportional to the slope. So, this brings us to the end of our discussion on summing amplifiers, integrators and differentiators. This also brings us to the end of our discussion on analog circuits. Hope you must have gained enough from these lectures. Thank you very much.